Hello everyone, my name is Dr. On. In this tutorial video, I'll go through this IB chemistry. It's for the International Baccalaureate Diploma program. This is for the higher level chemistry. This is TZ1 for the May-June 2021 exam series. So this is the paper 1. It's a paper 1 multiple choice questions. So which contains the most atoms of oxygen? We are just looking at the number of atoms. Of course, we know the number of atoms is related to the mole of atoms. So it's the mole of atoms multiplied by Avogadro constant. Having said that, instead of all of them multiplying by Avogadro constant, it is best if we just look at the mole of atoms, and then whichever one has the greatest number of mole of atoms, when you multiply by the same Avogadro constant, it's going to give you the most number of atoms for obvious reason. In this first option, we are given reacting mass here. So we need to work out the MR of O2. So the periodic table for IB paper is within the question paper itself. And that is slightly different from the usual periodic table that I do for my A-level chemistry tutorials. So we have to use this periodic table as it is given in the question paper. That is 16.00 multiplied by 2. That gives me 32.00. And the mole of oxygen atoms is going to be 2 times the mole of oxygen molecule. And that is because in one molecule of O2, we have 2 oxygen atoms. Then that is 2 times 64 gram of the molecule. So 64 divided by 32.00. So 2 times 64 divided by 32.00, I get 4 mole of atoms there. So that is the mole of the oxygen atoms. And there are 4 mole of this oxygen atom. All right, let's go through the other options. So what do we have here? We are given the molecules of O2. So if we are given the number of particles, in order to work out the mole of the atoms, we are just going to have 2 times the mole of atoms. If we want in terms of mole, what we can do is we can work this out in terms of the number of mole of the molecule, which is 6.02 times 10 to the 23 Avogadro constant. So 1.2 times 10 to the 24 molecules divided by 6.02 times 10 to the 23 molecules in 1 mole. But that is in 1 molecule of O2. How many mole of the O2 molecule multiplied by 2, because in 1 molecule there are 2 oxygen atoms. So 1.2 times 10 to the 24 divided by 6.02 times 10 to the 23 multiplied by 2. Again, I get 3.99, which is give or take around 4 mole. So 3.99, that's around 4 mole of the oxygen atoms. Now to the next one. So these are multiple choice question. We better work a lot faster, right? So the MR there. So 12.00 times 3 plus 5 times 1.00 plus 16.00 times 3. That's 89 there. So am I correct? Yep, it's 89. So 89.00. So 64 divided by 89.00. That is going to be the mole. The mole of the oxygen atoms is going to be the mole of this substance multiplied by 3, because I have 3 oxygen atoms in 1 molecule of these. So 64 divided by 89 times 3, I get 2.16 mole of oxygen atoms. Last but not least, what do we have? We're given the molecules of this whole thing here. So we're going to find the mole of it first. So divided by the Avogadro constant. So that is the number of mole of this substance, and I multiply by 3 because I have 3 atoms in 1 molecule of this C3H5O3. So just keying that onto the calculator, and I get 5.98. Give or take, there is 5.98 mole of oxygen atoms. Comparing all these 4 values, 4 mole, 2.16, and 5.98, very clearly D is going to be the greatest number of mole of the oxygen atoms there. Question number 2, we're given these masses of carbon, hydrogen, as well as oxygen. Now we're asked to find empirical formula. We know the empirical formula is the simplest ratio of atoms. So in a way, we are doing carbon, hydrogen, and oxygen. So what you have there is these are masses that are given already. So you're going to find the mole. So that's 24.0. This is divided by the relative atomic mass as given in the IB periodic table, and that is given as 12.01. So this is 3.0 divided by 1.00. This is 1.6 divided by 16.00. So moving that onto your calculator, 24.0 divided by 12.01, I get 1.998, that is roughly 2, obviously. This is 3, so 3 divided by 1 is 3. 1.6 divided by 16 on the calculator give you 0.1. And to find the simplest ratio, you need to divide the whole thing by the smallest number. So 2 divided by 0.1, this gives me 20. And 3 divided by 0.1, this gives me 30. Am I correct? Yep, okay. And then 0.1 divided by 0.1, this gives me 1. So we can say C20, H30, and O1. So that answer has to be option A there. Question number 3. So we are asked to find the volume of oxygen in dm cube and also at standard temperature and pressure when you burn 5.8 gram of butane. So butane is C4H10. We are given this reacting mass. So very importantly, we need to find the MR, which is the mass for 1 mole of the substance. So that's 12.01 times 4 plus 10 times 1.00. And just pressing down to a calculator. 12.01 times 4 plus 10 times 1.00, I get 58.04. But in reality, I don't really have to work it out because what we could see there is that is already at the bottom there. So 12.01 plus that, it seems like there is nothing wrong with the MR. So the MR is as it is. So what we could say is, you see from my other topical playlist on mole calculations, I'm a big fan of using this fraction method. So I'll show you what I mean. The mole of oxygen is what you want, divided by the mole of C4H10, the information that we need, that we have, okay? And then this is mole of something of a mole of something. So from the balance equation, 13 mole of oxygen divided by 2 moles of C4H10. So just, put in the mole ratio. This is from the balance equation, whereas the other side is going to be from the actual amount. So on the top there, based on my label on the left, I've got oxygen, mole of oxygen. So here, I want the volume of oxygen at standard temperature and pressure. That is to do with the 22.7. So those 22.7 is the molar volume. Molar volume of gas at STP is given as 22.7. This is dm cube per mole. 1 mole of any gas occupies this volume in dm cube at standard temperature and pressure. So this is the volume of oxygen divided by 22.7. This is the mole of oxygen at standard temperature and pressure. At the bottom, I have the mass, so 5.8 divided by the MR or C4H10, which of course I have already, and that is actually basically this whole thing here. So that thing there, divided by that at the bottom, and close that bracket. So these are values, So what we do really is we move that up there. So the bottom bit move up there. So 13 over 2 multiplied by 5.8. I'm just going to write the MR or C4H10, which of course basically means the whole of these, which there was no problem with for all the options. And this is volume of O2 over 22.7. The next thing we do is really we move up the 22.7, and we will get volume of oxygen as 13 over 2 times 5.8 over the MR or C4H10 multiplied by 22.7. This one will be in dm cube because what we did earlier was this was in dm cube per mole. So this is in dm cube. You wanted the volume in dm cube. So this expression is perfectly fine on its own without the need for any 1000 or multiply by 1000 or divide by 1000. This is definitely the wrong stuff. What else can I say? We have the 13 over 2 ratio because we don't move this ratio around, we just move this up there. So it has to be 13 over 2 as well. And we see here, our problem for option A is this 13 times 2. So A is wrong, D is wrong, and 2 over 13, that is wrong. So you can only have one answer, which is option B there. What do we have in this question? Relative molecular mass of bromine according to the following mass spectrum. What we could see is we see 3 lines, and then we get a M, we get a M plus 2, and we get a M plus 4 kind of line there. Because this is 160, this is 170, this is 180. So if that is 160, this is 162, this is 158. And then those must be for the molecule. the molecule of which contained 2 bromine, and you can get 2 combinations, which is 79 bromine, 81 bromine, 79 bromine, 79 bromine, and you could get the other one, which is going to be 81 bromine, 81 bromine. So the middle thing there, which is the same as 81 bromine, 79 bromine, is just the permutation difference there. So there's 81 bromine, 81 bromine, and I said this is M plus, there's M plus 2, that is going to be M plus 4 there. What do we have? We want to find the relative molecular mass of bromine. So this thing here, you can see is 1:1 ratio. That is because the isotopic abundance of 79 bromine and also 81 bromine, isotopic abundance is around 1:1 there. So what do they want here? They want the relative molecular mass of bromine. So we are not looking at the atom, we're looking at the molecule because of the definition of molecular mass. They don't want the relative atomic mass. If you just look at that, that will give you the relative atomic mass. Both of them have their own specific definitions as stated in your IB syllabus. Now looking at the molecule, so if we look at these, this give or take is around 50%, and then this is around 100%, and this is around 50% again. So what we get is the mass number multiplied by the percentage. So 158, well, it's not exactly 50%, I guess 52 is probably right. 158 multiplied by 52, and then what do I have? And then I add it with 160 times 100%, and then I have 162 times 48 because that plus that give me 100. And I gotta divide by the sum of all the percentage, which in this case is not 100%. It's just gonna be the sum of all of these. Sum of the percentage, not sum of the masses. Sum of the masses is wrong. You divide by the sum of the percentage. So A is going to give you a sensible number, which will be around 160 because these and these will cancel out due to the averaging process. And they are 1:1, give or take roughly. These are atoms. We don't include them in the relative molecular mass. If we just do the atom, we will get what we call relative atomic mass. But look at the bottom. What do we have? We have 11% because these are the molecule as well as the atom. So, you know, not really quite valid there. All right. Actually, it's okay. It's okay because you will get somewhere in the middle. You get 80 because there's the relative atomic mass of bromine atom. Question number 5, very straightforward question. You have p orbital. This is not mixed, it is not hybridized, it is simply dumbbell shape. Dumbbell shape, and they have to be equal in size on both ends because not A, because this is a hybrid orbital. You can see one side is bigger than the other, so it's already been hybridized. This is a pi electrons, pi bond, so it's a pi orbital, where you have rich in electrons above and below carbon, or even carbon oxygen. Instead of just carbon carbon, you can get carbon oxygen double bond, carbon carbon double bond, etc., etc. This is your spherical s orbital. So it's as spherical once you draw in the 3-dimensional axis there. Question 6. This one shows the first ionization energy, consecutive elements in the same period. So this trend will repeat from one period to another. We see an increase, a slight decrease, an increase, and then a second decrease. So this is the first decrease, and then this pink one, this blue one, sorry, is going to be the second decrease there. So the second decrease is not so big. The first decrease is actually not so big as well. In general, first ionization energy increases, but you get 2 small drops. The first drop is between group 2. Let me check your periodic table because yep, so you use the numerical value, so between the group 2 and group 13. And then the second drop is between your group 15 and group 16. This is from your P3, where you have 3 electrons in the p orbitals, to your P4, and you have 4 electrons. So this thing here, the paired electrons will repel more than the unpaired electrons. You get a small drop in ionization energy, as it is much easier to remove from these electrons here, because you are removing an unfavorable repulsion. Whereas this group 13, you are removing from the p subshell. If you think about the S and the p subshell, so p subshell if you are an electron in the p subshell, you are more shielded by the electrons in the s subshell, okay, and in a way you are further away and more shielded, therefore you are less attracted to the nucleus, and that's why it's slightly easier for you to ionize from the p subshell than from the s subshell. You're going from the s block to the first element in the p block, so the electron that you're removing and doing the ionization is from the p subshell there. You're looking at x versus y, so you're looking at the first reason, not the second reason. So it has got something to do with different sub-level. So removing the electrons from the 3p subshell, further away from the nucleus, more shielded compared to removing the electrons from the s subshell. Therefore, slightly easier to remove there because weaker net force of attraction to the positively charged nuclei. So it's got to be A there. It's got nothing to do with that, or that. Okay. And I mean, Y does have a greater nuclear charge, but it doesn't explain it because you haven't talked about the shielding effect as well as the different subshell where you're removing the valence electron from. Question 7, we are looking at the same electronic configuration as argon. So we're looking at 1s2, 2s2, 2p6, 3s2, and 3p6. Br minus, this is way down. I think this one is period 4 because chloride comes from chlorine, which is period 3. This is period 4, this is period 3. A is not going to be the answer. Ca2 plus, so calcium has 20 electrons because it has 20 protons. So now when you form calcium 2 plus, the atom will have lost 2 electrons. When you lose 2 electrons from the calcium atom, you're going to get 18 electrons. So 20 minus 2, 18 electrons, and guess what? It's going to look just like argon. So B is our answer there. Of course, since I'm doing tutorials, I'm going to go through all the options and prove to you they are incorrect. So aluminium started out with 13 protons and therefore 13 electrons as it is an atom. When you form Al3 plus, you have lost 3 electrons. So therefore we can think about 13 electrons minus 3. 10 electrons is the configuration of neon, not argon. Si4 plus is a period 3 element. So just like aluminium, when you lose the 4 outer shell electrons, you're going to have neon configurations. Both of them do not have argon configuration there. Question 8, on going down group 1, which trend is correct? So these are group 1 metals, and having said that, they have giant metallic structure. So when you think about your giant metallic structure, you have your cations, and then you have your sea of delocalized valence electrons. After the metal atoms loses the outer shell electrons, these are your delocalized valence electrons, and these are your cations. So you do not have anions because all these electrons simply come from the outer shell of the metal atom, and they shed it away to give you cations with fully filled outer shell. And then you have a force of attraction, electrostatic force of attraction between the cations and the negatively charged electrons. So these are called metallic bonding. So the stronger the force of attraction, the more energy is required to melt or boil the group 1 metal. Now in terms of this force of attraction, down group 1, what can we say? Down group 1, your size of cation is going to increase, but you still have the same charge. So you still have the same +1 charge. So what else can we say? They are going to delocalize the same number of valence electrons. So same number of valence electrons delocalized. So that is really saying that those are not the factors that are changing. Realistically speaking, it's the size of cation getting bigger. And if the size of cation getting bigger, we can say the charge density of the cations is decreasing because the charge is the same, but the size is getting bigger, so charge density is getting smaller. Therefore, we can say the metallic bond is getting weaker. And that is the explanation for the metallic bond strength going down group 1. If that is getting weaker, your melting point will decrease and not increase. And then in terms of reactivity, you're losing outer shell electron that is further away from the nucleus and more shielded, and therefore reactivity would increase, and your valence electrons become less attracted to the nucleus. Therefore, they are much easier to remove and ionize, and it has to be electronegativity because we know fluorine is the most electronegative atom, and it decreases that way. It decreases down a group as well, so therefore electronegativity will decrease down group 1 also. Question number 9, we're looking for the overall charge of this complex. So this is a chromium 3. So if you have chromium plus 3, and then you have 4 times water, each water has no charge, and therefore however many water you have also have no charge. You have a chloride ligand, which is -1 charge, and you have 2 of that, so it's -1 times 2 is -2. So plus 3 and no charge, plus 3 minus 2 is going to give you a +1, so X is going to be 1 plus overall. Question 10, you are looking for a compound which contains both ionic and also covalent bond. Mg2 plus O2 minus, that is just going to be ionic bond, so not that. CH2Cl2, if I draw the 3-dimensional geometry, there will be a tetrahedral, 109.5 degree, 4 bond pairs, and 0 lone pairs, tetrahedral geometry. Not that they asked for that, but that is going to be fully covalent there. And when you look at CH3COOH, so that is your ethanoic acid, that is totally covalent. Of course, it can ionize in water, but you don't have water in here. They never say it's an aqueous condition. They just say it's just molecule on its own, so you do not get the dissociation unless you have water. It's got to be NaOH, because when you think about NaOH, you have Na plus and OH minus. Inside the OH minus, what you have there is your covalent bond, but the interaction between the positive ions and the negative ions, that is going to be your ionic interaction. So D is the answer. Question 11, we are looking at something which is most likely to be ionic. We know that ionic compound has a giant ionic lattice structure, and as a result of that, you will have a high melting and boiling point. Having said that, B and C is definitely wrong based on the melting point. And then we're looking at solubility in hexane. Hexane is a non-polar covalent molecule. So we are looking at an ionic compound which is going to be insoluble or low solubility in hexane. But you look at A and D, having crossed these two out, there is no separation between these two properties. Therefore, we have to look at electrical conductivity of the solid. In the solid state, your ions in this case, they are not free to move at all. They can only vibrate about fixed positions, and therefore they cannot conduct electricity as a solid. They're not going to have high conductivity. They're going to have low conductivity there. So D is the only answer. Number 12, you're looking for something with delocalized electrons. That means electrons are not really localized in the shell. We have this thing which is ion. This is a carboxylate, and then we have carbonate ions, and then we have phenol as a molecule. So we are not looking at a phenoxide ion. This is a phenol molecule. So carboxylate is a very obvious choice, so you can definitely delocalize these electrons and give you the resonance structure, the alternative form where the double bond move around. So this is the resonance structure for option 2. For option 3, you have the carbonate ion, trigonoplanar geometry like this. What could happen is that could move around, and then basically we call that delocalization, and that's gonna give you that. And of course, I can delocalize a second time. Where is this? I can delocalize a second time this way. If I move the lone pair on this oxygen and go to the other one, then I get O minus, and double bond there. So I get 3 different structures from this carbonate ion as a result of delocalization. We can delocalize phenoxide ions, but then when you look at phenol molecule, the OH activates the benzene ring and increases the electron density inside the benzene ring, but it does delocalize the electrons into the benzene ring. Actually, in a way, it does delocalize the electrons into the benzene ring, because when you delocalize the electron into the benzene ring, it's not very available for doing condensation, for forming ester on the phenol. That's why you need acyl chloride to react. But you also activate the carbon number 2, carbon number 4, and carbon number 6 towards electrophilic substitution. So I think 2 and 3 is definitely correct there. So A and B is definitely wrong because they don't include 2 and 3, both of them. In terms of whether phenol have delocalized electrons or not, this electron does get delocalized into the ring. It pumps the electron into the ring and increases the electron density into the benzene ring. Okay, so we are looking at option 1, 2, and 3 there. There must be option D. Question 13, in which series are all the carbon atoms sp2 hybridized? sp2 hybridized means one of the s and two of the p, so it means one p orbital which is not hybridized. And what this also means is this sp2, so you have 1 plus 2, so you have 3 electron pairs. And we're looking at shape of molecule. If you have C2H2, this is C2H2. This one here is considered 1 sigma. We call it a sigma bond because you have a triple bond there. When you have a triple bond, you can have maximum of 1 sigma bond, and you will have the remaining 2 covalent bonds being a pi bond. This is a sigma bond. So we look at around carbon. We have 1 sigma plus 1 sigma, that is 2 sigma, therefore 2 bond pairs. You also have 0 lone pairs because carbon have 4 outer shell electron. It forms 1, 2, 3, and 4. Okay, it uses all 4 valence electron for forming covalent bond. So it's got no lone pair at all. 2 plus 0 is 2 electron pairs. What you want is 3 electron pair in order to have sp2 hybridization. C2H2 is not what we're looking for. And having said that, A and C are out. So what else can I say? I can definitely cross out C2H6 without checking further because that is alkane when you look at C2H6. So I've got to use a bit of the space down here. So C2H6 around each carbon, what you have is you can count the number of sigma covalent bonds. 1, 2, 3, and 4, the green color one. Around each carbon, 4 single covalent bond, 4 sigma, 4 bond pair, 0 lone pair, as the carbon use all the 4 outer shell electrons for bonding. You're going to get 4 plus 0, which is 4 electron pairs. What you want for sp2 is 3 electron pair because 1 plus 2 give you 3 electron pairs. So this one is carbon sp3, 109.5 degree tetrahedral geometry. Whereas C2H2 is a carbon sp hybridization, 180 degree linear geometry. You're looking for C2H4, which is an ethene, and looking for H2CO, which is an aldehyde. So this is a CO, H and H. So there's your sp2, trigonoplanar, 120 degree there. And this is a carboxylic acid, also having this trigonoplanar carbonyl CO double bond center there. So question number 14, what is the enthalpy change in joules? So very clearly they have bolded it so that you will be reminded about it. You have 5 grams of water and you are heating it from 10 degrees Celsius to 18 degrees Celsius. So the heat capacity of water is given as 4.18 kilojoules. So keep an eye out for this. And this is per kilogram and this is per Kelvin. Now first of all, our change in temperature is 18 degrees Celsius minus 10 degrees Celsius, which is 8 degrees Celsius. But the change in temperature in degrees Celsius is exactly as the same as the change in temperature in Kelvin because these are not absolute temperature. They are just difference. So, if you have 18 plus 273 and then 10 plus 273, you take the difference. The 273 minus 273 will cancel out. So the change in temperature in degrees Celsius equals the change in temperature in Kelvin. That much is pretty obvious. So 273 plus 8 is going to be incorrect there. So C and D are out. You are left between option A and B. That is where we need to think very carefully about this 5 grams of water. So if we have Q equal to mc delta T, where Q is heat energy, the M of water is 5 grams divided by 1,000. So 5 times 10 to the minus 3 is kilogram. And then you multiply that by heat capacity, which is 4.18 kilojoule over kilogram, and then over Kelvin. So it's per kilogram per Kelvin multiplied by the heat change, temperature change by 8 Kelvin, you will see that 8 Kelvin and 8 Kelvin cancel, kilogram and kilogram cancel. You're going to get an answer which is 5 times 10 to the minus 3 kilojoule, but you want your answer in joule. So, you know, realistically speaking, I need to multiply the whole thing by 1,000, so that to convert the kilojoule into joule. And once I've done that, the 10 to the minus 3 and 10 to the power of 3, they will cancel out. And once they cancel out, I'll be left with 5 times 10, 4 times 18, 4.18 times 8. So realistically speaking, I do not have that 10 to the minus 3 because the unit will cancel out when I multiply the whole thing, which will give me kilojoule. But I multiply by 1,000 to convert it to joule is required. So 10 to the minus 3 and 10 to the 3, that will cancel out. That means that cannot be the correct answer. Only A can be the correct answer. That's very confusing. Very good question there.